So just as a warm-up exercise to get a sense of how a tree structure can efficiently support such operations, I would like you to think about how we would implement nearest in an efficient way. So I've given you some example inputs, and here is the binary search tree, the bushy version, that is built upon the set I gave you earlier. So your goal is figure out an algorithm that would support nearest in. So you might, for example, try and find the nearest of, I don't know, 5.7 or something, and just see what happens. What algorithm would you use? So the very naive algorithm is just look at every single node. That's not very interesting. I want you to do something better. So think about that for a second. Okay, so the algorithm that I have, and I'm not going to prove to you that it works, is pretty intuitive. And the basic idea is you just search for the thing you're asking for. So for example, if I want to know the nearest item to 5.4, I'm going to search for 5.4 in the tree. And then I'm just going to record the closest item I see along the search path. So for example, the 5.4 example I was giving earlier, I would start at the root and I would say, well, 11 is the closest thing I've seen to 5.4 so far. Now, if I want to get closer to 5.4, I shouldn't go this way. Right? 5.4 is less than 11, so I really ought to go to the left. So I get to 6 and I say, well, that's actually closer to 5.4, so I'm going to note that as my new best. Okay, at this point, if I wanted to find a number that is closer to 5.4, I could either go left or right. However, I'm only going to go left, and in this case, I will land at this 4. And well, at this point, I look at the 4 and I say, oh, well, 5.4, that's actually farther away from this current node 4, so 6 is still my best. So I'm leaving it here green. 6 is still the best. And then lastly, I need to keep looking for something closer, so I go to the right. It turns out, 5 is a little bit closer. And so what I got here is that by exploiting my binary search tree structure, it took less time than looking at all of the values. Now you could actually also use similar ideas to efficiently support select, rank, and subset. We're not going to talk about them in lecture, but I just want to give you this as a warm-up so you can understand why trees can be really helpful, not just for add, contains, and delete, but also other operations you might imagine trying to implement. That brings us to what we're going to work on today. So we have only discussed one-dimensional data. That is, all of our data can be compared under some total order, like 1 is less than 3, 3 is less than 6, and so forth. Or if we're thinking about the alphabetical order of strings, cat is less than zebra. Or if we're thinking about string length, if would be less than zebra, 2 letters versus 5. But not all data is single dimensional. And we'll see that whenever we get to the next video. I'll give you some examples. And what we'll see is that if we want to support multi-dimensional data, we need to tweak our idea of what a search tree ought to look like so that it can function efficiently on multi-dimensional data. That is, if I want to start supporting operations like subset or nearest, there's going to be some design tweaks. I think they're pretty interesting.